Hello, welcome to CM Videos. My name is Dr. Michael Okereke. Welcome you to another video in the series of videos I'm making on representing the volume element modeling. And this particular video is targeted at this, which is called the particulate reinforced composites. And in particular, we're looking at a particulate reinforced composite that has a compact density, so it's very well compacted, and so that introduces some difficulties in terms of how you're going to model that, because you then need to capture this very high volume fraction of the inclusions within the domain. So this is the object of this video, so let's jump ahead and begin this modeling. So the outline that we're going to work with in this video, we'll start off with, first we're going to introduce a little bit around this idea of a highly compacted composites, particulate composite, what are particulate composites, and then I'll quickly tell you how to set up the model in ABAQUS, and then after that we'll review the simulation results just to look at the stress strain, look at the contour plots, and then finally we're going to also extract stress strain data to see if we can understand something about the quantitative information around this kind of composite materials. So by way of introduction, what are particulate composites? So I've given a definition here saying that these are basically composites in which a matrix medium, generally with a low strength, is mixed with particles to improve their overall properties. So that's the very classic definition of what a particulate reinforced composite would be. A matrix medium reinforced with particles. This is again something like laminated composites, where you have laminars, fibers that are oriented along the main axis of loading. So that's a different kind of scenario. Or maybe a textile composite where the inclusions are basically woven. In this case, you have particles that are distributed within the domain. A typical example, quite a common example of a particular composite is this Aluminium Silicate, which has basically an aluminum matrix with silica. Silica particles a bit like sand particles, something like that. So you have those kind of particles, mix them together, enhance their properties, and then you use it in different applications as you would want. And I picked up a micrograph to kind of illustrate this principle, especially for a compacted composite. This is not an aluminum silica composite, rather it's a zirconium silica composite. So if you look at the properties of this material, so this is where I got the information from. So basically the zirconium is the matrix medium, and silica is basically the reinforcement associated with this kind of system. So this is kind of what we have with this material. A highly compacted composite, in the way that I'm using to describe it here, would basically consist of the main particles in their big sizes. So they've got these big size particles, which in their RVA modeling, as well as the small particles. Because what creates that compaction is the small particles that are filling on all the gaps that the big particles couldn't fit in. And this is why if you go back a bit to the micrograph, you would see that you have big particles and tiny particles, and that creates this compaction, therefore making for a high volume fraction of inclusions, enhanced properties, and a really compacted, highly compacted composite. So this is what we are going to be looking at in this video. So I've taken this information from this source, this journal article. Again, you can always go back and look at this journal and see. In this case, it's described as a binary aluminum silica composite, simply because the inclusion sizes are basically two. You've got a big size and a small size, so it's binary. In some cases, you have multiple particle sizes that you could also use in your simulation. So in this case, the two particle sizes that we're looking at are the 15 micron particle size that we see here for the silica big, and the 8 micron particle that we see here for the silica small. Okay, now the case study that we're going to be using for this video is basically this high compact aluminum silica composite. And what would the virtual domain look like? So the way that I'm going to create this model soon, as I show you in ABAQUS, would be there will be a silica big, which is basically the fibers that are the inclusions that are big in size. That is a 515 micron diameter inclusion. And then there will also be another instance which will be the silica small. So these are the smaller diameters. So they are going to be created separately and then kind of be mixed together. And of course, we've got the matrix, which is the space that those two leave behind. So this is the 3 stages for creation of this domain. and that's what we're going to do. So of course the next step in doing that is to try and mix them up. So you start off first with the matrix, and then you include the big size fibers, and then finally you include the small size fibers, and therefore with this you are creating this compacting approach. This is typical what you will do if you're manufacturing this medium. You create big size particles first, and then if the system is not compact enough, then you start breaking up tiny particles and start filling up all the gaps. Shake the domain until you're having a compact domain. So this is kind of what we're trying to do here. So you start off with the matrix medium, then you fill it with the bigger particles, and once you have those spaces that are left behind, you also fill it with the smaller particles. And even if that is not possible, you can keep adding tinier and tinier particles so that you can have more than just a binary arrangement of particles, but something much, much bigger than that. So that's the principle that we're going to use in creating this video. Okay, so the first question that would probably need to know is how many of these big size particles will fit within the domain that we're looking at. So the domain we're looking at is a domain of 120 by 120 micron in size. And so using this equation, we can work out the number of fibers. So first, because my overall intention here is to create a 60% inclusion and volume fraction, so the bigger size can accommodate nicely a 45% inclusion in the way that I've modeled this. So first, I'll create a 45% inclusion for the big diameter fibers, silica, and that gives me 37 fibers or silica particles. And then we can move on to the smaller silica particles, which will be the remaining 15% to make up an overall 60%, and that gives us 43 fibers according to it. So you could see here the diameter, the radius of the inclusion is 4, and 0.15 being 15%. So if you mix 15% with 45% here, you get an overall intended volume fraction of this system to be 60%. Of course, you can keep going on ahead to do this by adding tinier and tinier particles and then increasing the volume fraction, but we are working with a 60% volume fraction in this problem. All right, so the other thing that we need to also think about is how are we going to create this? So I'm going to use montcarlgen, which is this software that I developed for creating random inclusions within a predetermined RVE domain. The inclusion usually is for one size of inclusions. Maybe future releases of this code will allow us to have multiple diameters of inclusions within the domain. But for now, we're working with only one size of inclusions. And so I'll use that to create the first category of inclusions, which is a silica big. And then the next bit, which is the tinier particles, will be done manually within ABAQUS CAE. And of course, the metrics will also be created manually. So that's the approach that we're going to use. Now, thinking about the materials that make up the system. So the first thing is that I need to think about the elastic properties of the material. So the aluminium properties are given, and the particulate system, which is the silica properties, are also given. And I specified where I got that information from, which is the paper that I mentioned earlier on. So it's got all those properties. So again, do dig up that paper and use to review if you are interested in this. Now, the second aspect to it is because I want to allow this matrix to show nice plasticity and even damage evolution, so you have a more realistic representative behavior. So again, I found another paper which is specified here that give you the properties of the aluminium, and in this case I'm modeling the plasticity of the aluminium using a Johnson-Cook material model. So this gives us the properties of the metric of the according to Johnson-Cook, and even also the damage properties. So we're going to combine these two things within the modeling as we build what we're looking at. Now, the final thing that I want to do also, because of the nature of the domain and the idea of trying to minimize the effect of boundary condition, I decided to use a periodic boundary condition to do this 2D simulation on this highly compacted aluminum silica particularly reinforced composite. And so what does that mean? Basically, I should allow the domain to show a periodicity of deformation. Okay? If you're interested in periodic boundary condition issues and all that, please I've put in the card a list, a previous video that I've done on how to set up automatically periodic boundary conditions. So please do look up that and see if you can use it to understand more what we are trying to show here. Okay, so then of course the other thing that is important is to also show how you apply your boundary condition. The other thing that I need to also mention here is that if you're interested in how to extract stress and strain data from a system like this, again, there is a video in the card that I've made of how to extract stress and strain data within a periodic boundary condition enabled domain. The software, again, that I will use in doing this is called pbcgen2d. Currently, there is a pbcgenlite, which is limited in the extent of what it can do. For this one, I'm going to use the full version. And again, please do look in the description section for the full version of pbc2dgen and how you can use it to run simulations for quite complex domains with, high density of meshes and that. So we're going to use the full version of pbc2dgen, pbcgen2d, the full version for it, not the light version. Okay, the final thing that I need to say before we jump into ABAQUS to set up this model is how the loading analysis would work. So basically, our loading analysis will consist of loading in this tensile case in this extension direction. So that's what we're going to be applying on this domain. And so let's jump into ABAQUS and begin this modeling. All right, here we are in ABAQUS. So what we're going to do now is to show you how to set up the model and then run it. So we're going to use a script to do that. So this is a script that we're going to use, okay? So if we copy that script and then we'll go back into ABAQUS. So you go to the second tab at the base here and paste that information. So what it will do now is that it will run through and generate the first version of the code, which is the big silicon carbide. I've already set up the model here, but I'll just show you how this is done. So if we go into here, so we've got the fiber system. So if I rename this, so I'm going to call it big silicon carbide, okay? And then I'll create a copy of that. So I'm going to call that small silicon carbide, all right? So, and then with this small silicon carbide, so if you open it, you see here, then open all this. So this is the section cache. So what we're going to do is, because we don't need these positions in the way they are, so I'm going to delete all that, okay? But interestingly, I still have my locations in place, where they are in this diagram. So this is fine. This is okay. So we're going to use the locations here to position the new fiber. So I'll just create a new fiber. I'm going to dimension this new fiber, and I'm going to call it, so let's say it's 4, because it's a diameter of 6, so it's 4. So what we're going to then do next is to just create a linear pattern of these fibers. Okay, so you've got as many of that. So basically as many as you can have, as you would like, so that you could, fit them in within the window. So we kind of know what we're looking for. We're looking to fit as many of these fibers in the window. So basically, the argument, we are saying that we need to have about 42 of these fibers fitting into that window. So you can create 42 particles in this window, and then you start translating them. So how do we translate them? So basically, you click on this and say, okay, I'm going to move this one from where it is to, let's say, a position like that. So that goes into that place, you cancel, and then you come back again. I'm going to move this one from where it is to a position like that. So this is a manual way of creating this new inclusion from where they are to where you can find spaces. So hopefully you're not doing it with a lot of particles in the system then, because it's going to be quite an effort to do that. So we'll do the same. So you copy one again from there, from here, until you get into the position that you're interested in. So once you've done all that, so I'm going to basically, so we are going to delete all that. So once you've done all that, then you click OK and click Done. And so it comes up here, and then Future Regenerate. So you can see it's created the new particles in the positions where they need to be. I'm going to use a complete model later on that I've already done to illustrate this, but let's just carry on from here. So once you've got that, so basically we've got this, we've got the metrics, we've also got the big silica, and then I can delete. So if you go to the assembly of this particular model, so we have all this set up, so we need to resume those two ones and then delete the composite that was generated previously. Okay, So that means we go back here and delete the composite that was generated previously. Okay, so basically we have fibers, which is the big fiber. We've got the matrix. So the only thing we don't have is a small fiber, which we have now. So we've got all three in their window. So small fiber, big that. So if we combine all that and click on this, so we can now say, okay, aluminum silicate carbide, return, and you select all those continuously. So basically what you now have is a complete model. So if you go back to your part, you can actually see aluminum carbide ore, which consists of the matrix, consists of the big fibers, and also consists of the few small fibers that we have set. Then obviously we need to extrude cut. So what we need to do with the extrude cut here is to start off with this small one, and then we also create a big one, and then click done. So this creates the material that we are interested in using in this case. Okay, so if we then look at the original model that I've done, how that looks. So once you've created a full model, so this is how it will look. So this would be the model that consists of all the fibers, and all the big ones, the small ones, everything will kind of look like this. So just still as part of illustration, so the next thing we need to do once we've done that is to go and look at the materials that we need. Okay, so currently we have fiber and matrix, so we can rename that or we can leave that. We know that the fiber is basically the silica, so we could call it here silica, silicon carbide. No, so we go here and call it silicon carbide. So that's fine. So what do we want at the elasticity of the silicon carbide? So it's 470 e to the power 9 and 0.142. We can include a density to silicon, which is 3120. So the matrix is really aluminum. So the properties of aluminum that we are using in this model, so 62.59 e to the power 9 and 0.33. So that's the properties of aluminum. In terms of plasticity of aluminum, we would have a different value. So we are looking at using a Johnson-Cook model for it. So the properties of the Johnson-Cook will be 167 e to the power 6 and 596 e to the power 6, 0.551 for N, C is, and then M is 0.851, The melting point of aluminum is 660, and the transition temperature is any temperature at which yield stress. So we could use 20 or something like that, or maybe above that. So, but it doesn't matter because we are not including temperature in this. It's not a temperature sensitive model, so this part of the model will not come in. So in terms of rate dependence, so we're going to look also for the Johnson-Cook rate dependence, and we're looking for the C values. So the C value is 0.001, and then epsilon dot can be 1. Basically, it's a reference strain rate. Initial strain rate. So something very low can be important for this. I'm going to use 1 for it. So this is our rate dependence. The other thing we want to include is a damage due to Johnson-Cook. So there's a Johnson-Cook damage associated with this model. So again, our Johnson-Cook damage says 0.0261 for the first case, and then the next one is 0.263. The third one is minus 0.349. The fourth one is 0.147. D5 is 16.8. Melting temperature is 660. I'm using transition. Reference strain rate is 1. So this is fine. So once we specify all that, so we have our properties. So what we now need to do is to do so in the section assignment here, if you double click there, so I'm going to press the matrix. Okay. So we know that this is a matrix, which will be the matrix section. Okay, and then all the other bits basically will be the fiber. So what we are going to do again is we select everything, click the matrix, press down, click control and click the matrix. So if you click the matrix, so what this will show you will release only the fibers. The matrix is deselected, and then the fibers are basically the aluminum cross section. So we can always check to see if we've done it right. So this is okay. So we have everything correctly the way. Then we now do the meshing. So if you double click on the mesh, so what kind of mesh? 1.1. So we could start with that. That's okay. So what element type are we interested in using? So our element type here will be a triangle, okay, and then we can mesh this domain. Okay, so we've got the domain, it looks all right. So the remaining parts we need to include in this model is to find, still with PBC, so we need to create a set. So I'm going to call my reference node set. Okay, so that means I'm going to pick all the corner nodes, pressing down shift. So we press all the corner nodes there because we're going to use it within our periodic boundary condition system. All right, so the other thing is that we'll now go to step. So we need to use a dynamic explicit for this because this is necessary if you're going to use a Johnson-Cook model. So I'm loading step dynamic, so something like that, you could use it. So dynamic explicit, so we can leave all those as default, as fine. History output, so our reference node history output, we need that because that's what we are going to use to plot our results. So it's based on set, so reference node set, so RF1, RF2, RF3, coordinate 1, coordinate 2, coordinate 3, U1, U2, U3. So these are the displacements. So that's what we are tracking in this simulation. Okay, so the next thing we now need to do once we found that and we've sorted out is to think about our boundary, boundary conditions that we want to use in this domain. Remember, with periodic boundary condition, you only use return nodes. So I'm going to say X back roller. So I'm going to apply a roller system on the back displacement boundary condition. So I'm only interested in what's happening at those 2 points. Okay, again, if you're unsure about this, please look at the video that I put on the card about periodic boundary conditions, the setup of them and all that, and that will help you. So the other bit is Y base as a roller support. So we go on here, so pick that point, press down shift and pick the other point. So that gives you that in the Y direction. So we've applied the boundary conditions and then we also need to apply our load. So I'm going to call it extensile load. It won't be an initial step anymore, it's going to be a loading step. Still a displacement base, we apply it right at this point. And because this system is 120 in length, so this will be, I'm going to just only do a 10%, so 12. With dynamic system, you need an amplitude. So we click on this amplitude function. So leave the name here, just use a tabular system, a simple, just monotonic loading, 0, 0, 1, 1 is okay. So we can always work with a monotonic loading. So this is fine. So we work with that. Okay, so we need to select it here. So this is that. So we've set up our boundary conditions, everything is all fine, and then we can go and try the model. So let's call it aluminium, okay, something like that. So this is fine. Okay, so what we are going to then check is where is our working directory. So we've got our working directory set up there, so we know that, copy that. Now open the model that you're interested in, which is this extents, write it to input. So we write that to input, okay? And then we'll go back and find where that information is in our code. Okay, so I found where this model is and I've copied it in, I've brought it into this environment where I've got pbcgen, gen. So there is a full version of pbcgen which is here. So this will be available for you to download to use subsequently. If you look at the download section, you find a link of how you can download and use this pbcgen, the full version. So basically we've got that, and what we need to do with the full version is to call it pbcgen full. So you enter. So what it will do is that it will look in the environment and find different input files. So here it says pick the ABAQUS input file that you want to use, which is this one. So you double click on that. So what it will now do is we'll run through, and like the Genlite version, it will run through and generate plots for us. So it gives you the plot of all the nodes and how it's demarcated them into the boundary nodes. And this is also the boundary nodes that we see around here in this window. So this is fine. And then at the end, what is most interesting is that it's created an input file for us. If you notice here that the node number is 13,683. So this pbcgen full version can do that, unlike the other versions that can't, that was only limited to 4,000 nodes. So we'll find where the model is saved, which is this test case. Okay, so I'll note the path name. Now I can go back to ABAQUS and import that model. What we need to look at here is the metrics. I did not specify a density for the metrics, and you need that. So let's just do that. So the density of aluminium, so if you go back to the density of aluminium, which is what we need, so the density of aluminium is 2660. Okay, so we've got that included in our model. We submit that model, it ran. So what we will have here is the result. So the next part of this video is to show you the kind of result. So we've already run it. Remember, in this new case that I'm talking about, I actually did it in a proper comprehensive way. So this is a full model with all the inclusions, exactly how they will need to appear. Everything is set up correctly as we did before. So in the result that we generate from this, so if we switch this to visualization module, I can then look at the tensile damage. Okay, so this is the result that you generate when you set it up in terms of von Mises stress. So what I'm going to do here is probably to go to Tools, Options, Common, and then I'll just show it as featured edges so that it will show just without the meshing. And we could then show maybe the plasticity, so you could see what's happening with this result. So this is just a plastic deformation showing the result that we're looking for. So it does show some interesting features. So you could see where damage is being accumulating on this domain. You see periodicity developed around, and everything is fine. The big particles, the small particles, everything is really undergoing a nice uniform deformation as you would expect. So the final thing that we need to do is to extract the stress strain data associated with this. So it's quite simple. So what we need to do is to create the XY data, work on the history output data that we want. Now we're going to have to use the values that we are asking for. So the coordinate positions first. So I press and drag down, and then press Control, click on the next one, and release Control and drag down. So basically I'm selecting the spatial displacement, the reaction forces, and the coordinates, and I'm plotting that. So you end up with a plot that looks like this. So clearly there is this stress strain data which shows something happening associated with the damage of the domain, which is all right. So we now go ahead and look at Excel utilities, current plot. Okay, so what this would do is that it would extract the properties, the raw data for all these plots that we've we've plotted, so that we can use it subsequently in our analysis. So this is what you need to do. Again, I have to say that this only works if you're working within a Windows environment. So once you've done that and you extracted the data, then we can copy it. So we can copy it into this spreadsheet. So this spreadsheet again will be included in the description section of this video. So please look out for that. So basically the data that we're looking at will be all the data that is copied and pasted up to this point. So that includes, so what does that data include? It includes the reaction forces, the coordinate positions, and the displacements associated with the system. Then we calculate what the force would be. Again, please check out this. Again, there's a video that I've made about this idea, so please do check it out on how to extract stress strain data for a PBC-enabled domain. Then this is a strain and this is a stress. So once you've done that and plot initially, so it will give you some data associated with the system. So I've now cleaned it up here, and you end up with a plot that looks like this. So the normal stress, the normal strain, tension, stress, and you get measure of the Young's modulus, the effective Young's modulus of the system. Remember that the matrix here was 70 gigapascal and the silicon was 470. So with the volume fraction and inverse rule of mixture, you can combine them and you end up with an effective Young's modulus of that. A strength value would change, because the material has damaged as well. So this oscillation is just simply because it's an explicit simulation. So you do get a little bit of this oscillation, but the trend is right. And so if you're going to use this data, you need to clean it up and work with the trend, so to speak. So, but that's maybe a subject for a different video. So this is what we will get for a system like this that is undergoing ongoing tensile deformation, for it to be said to be highly compact. So that's all I wanted to say in this video. Again, if you're interested in this kind of content that I'm making, please do subscribe to this channel. So if you're interested in this kind of video, especially on RV modeling, this is the video that you need to do on showing you how I've done this kind of thing for particulate composites, in 3 dimensions. And also the video at the top here is a video that will show you how to extract stress strain data for a PBC enabled domain. So thank you and see you in the next video. Bye-bye.